Reservoir outlet discharge control. Hello folks, my name is Rafael, I'm an engineer, and in this video I invite you to present the application of control theory to a reservoir outlet discharge, and to do so I brought this problem here. I'm gonna read the problem. The figure illustrates the discharge control system for the outlet of a reservoir by adjusting a valve actuated by a direct current motor. The output flow Q of T is controlled by varying the opening and closing of the valve, which in turn depends on the voltage applied to the motor's terminals V of T. The block diagram of the closed loop system model is shown on the board, where the gain Kp represents the proportional control responsible for promoting the variation of the supply voltage, and consequently the variation of the motor speed to drive the valve in order to obtain a desired output flow rate. The value of the proportional gain, Kp, to be designed for the system to operate with a critically damped response is... Alright my friends, let's go. Let's solve the problem. The first step will be to write down the closed loop transfer function, okay? So, the solution will be to write the closed loop transfer function of this model here, this block diagram. Alright, so firstly we're going to call G of S the multiplication between Kp, 0.25 divided by 0.25 times S plus 1, 50 divided by 50 times S plus 1. Then we write it Kp 0.25 divided by 0.25 S plus 1 and 50 divided by 50 times S plus 1. Okay? And if we conduct multiplication, we find that it is equal to 12.5 Kp divided by 12.5 S squared plus 50.25 S plus 1. Okay? So, we know that G of S is this, and then we're going to call H of S equal to 1, because here the output is being directly input here in the feedback loop. Then we're going to call H of S, the transfer function of the feedback element, equal to 1. Alright, then the new, okay, let me erase this, and then I'm gonna draw to you the new block diagram that we are going to use to find what the problem wants us to find. I left the problem in the description of the video, okay, the problem that I read. See there. Okay, so the new block diagram will be 12.5 Kp divided by 12.5 S squared plus 50 times 0.55 S plus 1, and this here Q of S, here the error, and here the feedback loop, and here the input U of S. Okay? We need to continue developing this to find what the problem wants us to find, and then we are going to use this. We are going to use that whenever we have, pay attention, whenever we have this and this, okay, whenever we have this, we can use a trick, okay? And here it is going to be R of S, and here C of S. I think that you guys have seen this in college. Whenever we have this, we can use this thing here. C of S divided by R of S equal to G of S divided by 1 plus G of S times H of S. Okay? Whenever we have this, we can do this, and this is exactly what we are going to do to find a simpler version of this, okay, to simplify that. And then, now that we know this, it is paramount that you know this before going to this. If you can assume that you know this, then we can go on, move ahead, and go to simplify that block diagram of there. Alright? So now we are going to use what was written here to simplify this, and then we get that Q of S divided by U of S is equal to 12.5 kp divided by 12.5 s squared plus 50.25 s plus 1 plus 12.5 kp. Okay? We are almost there. We are going to use a technique that control theory books give us to find what we want. But the problem asked us to calculate Kp for the system to behave in a critically damped way. The system has to be critically damped. So what does it mean to be critically damped? To be critically damped, this letter here, C, has to be equal to 1. And because C is the damping ratio, okay? And then we are going to write the system in the format like this: Q of S divided by U of S equal to K divided by J S squared plus B divided by J times S plus K divided by J. So this is what normally control theory books say that we should proceed as, alright? Okay, and this is going to be equal to Wn squared divided by S squared plus 2 times C times Wn times S plus Wn squared. Okay? What we wish is to find a configuration for this expression here. We are going to find a configuration for this expression here to fit in this format here. Okay, this is going to be the template, the format that we are going to use that control theory books give us, and we are going to try to adjust this into this. Alright, so what do we need to do to convert this expression into this expression? See that here what multiplies S squared is 1. And here is 12.5. Then what we need to do is to simply divide the numerator and the denominator by 12.5. And this is exactly what we're going to do. Okay, so save this. Okay, I'm going to erase, but these two expressions here will make sense for us to find our solution. Okay? And save it then. Okay, and now after divided by 12.5, we find that Q of S divided by U of S is equal to Kp divided by S squared plus 4.02 times S plus 1 plus 12.5 Kp divided by 12.5. Okay. What we need is to use this value here, 4.02. And if you remember, we said that B divided by J is equal to 2 times C times Wn. And when the system is critically damped, C is equal to 1. Then B divided by J is equal to 2 times Wn. Okay? And we're going to see that Kp, what we need, Kp is equal to Wn squared. Wn squared. And 4.02 is equal to 2 times Wn, where Wn is equal to 2.01. Okay? Are you guys understanding everything? And finally, using this here, we get that Kp is equal to 4.04. And in this way, the system is going to be critically damped. But before I finish this video, I want you to see what it means for a system to be critically damped. What does it mean for a system to be critically damped? I'm going to show you a graph that provides this information. Okay? Imagine that we are applying a step. The input is going to be like this. Okay, this is the input, and this is the output. This is the input and this is the output. So the input is going to be the step. Okay? I'm going to have a constant value of voltage here at the input. And imagine that we have an input like this to the system. Okay? And the output of the system is going to be of the form, if the system is underdamped, then the output is going to be of the form when the system is underdamped. When the system is overdamped, the output is going to be of the form okay? When the system is underdamped, there will be oscillations of the output. When the system is overdamped, there will be no oscillation. And here, C is between 0 and 1. And here, C is greater than 1. But when exactly C is equal to 1, the output is going to behave like this. Okay? The output is not going to present oscillations. It is going to be like this. It is going to go directly to 1, but with no oscillations. Sometimes the oscillations are welcome, but in this case the problem said that our interest is not in a system with oscillations. A system with C equal to 1, there will be no oscillations at all. Okay, my friends, this was the video that I wanted to make. I hope you guys enjoyed it and learned from it. I'm a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!